Good. Very good. All right. I did do something else. All right. Ooh. 3, 2, 1. Hi, everybody. I have a video for you. Our last one on both the theory of general relativity and a lot of information about black holes, which are super fun. I'm going to tell you right now, it's a ripoff. I'm lying to you already. This video will not tell you a lot about the theory of general relativity. And the reason for that is everything you need to know can be summarized briefly. The rules, the strangeness of special relativity behave in exactly the same way, except with specific relativity. We were 3, 2, 1. Hello, everybody. Here's our last video in the year 2020. I could play them in a different sequence in the future, but for our spring unit on the theory of relativity, here's our last video, and I'm going to talk mostly about black holes. They're really interesting. There's so much to say. I could make 4 videos, and a lot of hands-on things we can't do right now with distance learning. So I'm going to condense it. I'm going to add to it just this notion in terms of general relativity. Everything you've learned about special relativity applies. 1905, Einstein wrote his 5 papers that year. I think that the first one was about special relativity, and it basically considered how is it that space and time specifically, as well as some other phenomena, change or altered if, in fact, all the rules of physics are considered sacred and unchangeable. So, and specifically with respect to the speed of light or moving at that velocity, moving close to that speed, how do then space and time change? So this theory of special relativity had a lot to do with light and the speed of electromagnetic waves, or really any particle that has no mass. The theory of general relativity then changes. The focus becomes what happens around supermassive objects, things with incredibly intense gravity. I dropped something. So the something that I need. So the example of a black hole is an example of extreme gravity. Its density is so great that it warps this continuum of space and time around it. That warping would be sort of like maybe you could think about a heavy cannonball sitting on a trampoline or a bed, and that heavy, dense object would sink into the bed, the surface of the trampoline, or whatever, would make its own depression, and so then the surface of that bed or trampoline would then kind of form a cone going down, dipping into where that heavy cannonball sat. And other objects in the bed might roll in towards it. Now that forms sort of a low point on the bed. And in fact, the Earth is affecting the space and time around it and creating that kind of a depression. That's a 3-dimensional analogy. But now when we're talking about the theory of relativity and the way Einstein's brain worked, we're talking about 4 dimensions. And space and time are linked together. And so it'd be different. This is an analogy. For example, the Earth's mass warps space and time around it and makes sort of that kind of cone-shaped depression. And then the moon, which is smaller and about a quarter million miles away, is kind of circling in a straight line along that surface, but it isn't leaving because the surface itself kind of forms this depression or cone, and then going around the rim of it at some point at a constant velocity is the moon trapped in orbit. And so that now explains how gravity works in ways that Galileo and Newton never could. So we get things like time dilation. If you're closer to a supermassive object, time seems to be operating differently than in a reference frame farther from that supermassive object. And the observer closer to the supermassive object would experience time unfolding at a slower rate. So, length contraction, all those kind of things that we've talked about happen. Also, not if you're going some fraction of the speed of light, but also if you're just closer to some highly dense supermassive object, dark matter, like a black hole. That's it. We're going to watch a movie later, and I'm going to have you do some analysis on how they portrayed some of this stuff in terms of how accurately they understood the theory of relativity. And all you need to understand is the stuff we've discussed applies also to being really near something like a black hole. So let's talk about black holes. This PowerPoint has several little animations that weren't working earlier, seem to be doing great right now. And there's even some videos that are embedded within this. We'll just see if that plays. I'm going to just do one at the very end. So if it fails, we'll have gotten most of the way through this. I think this will be about a 40-minute slideshow. Here's a great quote saying quite simply, black holes are incredibly dramatic and exciting. The name is so mellow and unassuming you'd never guess it. Isaac Asimov, one of the great science fiction writers. We see black holes in cartoons and TV sitcoms and science fiction movies and books and comic books. They're just part of pop culture, modern culture, and our public consciousness. And maybe these are some movie titles or books that you've heard before. It's a pretty funny joke if you golf. Some really, really bad movies in science fiction have come out with the theme of relativity, black holes. All right, so even a sitting president, someone who was in office as the commander in chief of the United States, living in the White House, spoke once about how this is so fascinating. What's going on at the cutting edge of astrophysics? Not too long ago, kind of amazing. And maybe you remember in April 2019, just a year previous to the making of this video, people took the first successful photograph of an event horizon. It was in the news as the first picture of a black hole, which isn't honestly true. A black hole is, by definition, something we can't see. I'll talk about that in a little bit. But we can see its effect on space and time around it, and particular matter, objects in space. And this is an image of a bunch of matter swirling around the event horizon of this black hole. And as it does so, it's speeding up and accelerating, going faster and faster, so that it's tens of millions of degrees hot. These are now probably mostly just individual particles and atoms, screaming hot and therefore giving off heat and other kinds of electromagnetic energy like radio waves. And 200 scientists around the world work together using about 20 land-based radio telescopes and synchronize them and overlap their data to create this image here. Now, here are many really cool videos that are available for you on YouTube. I would have incorporated them in my lecture in our class. We'd spent a week or so on black holes and shown you many of them, but you can check them out on yourself. The first one is a 5-minute video explaining that the process through which that first image of a black hole was taken, one I just showed you. The second one there is a hilarious comedy sketch about black holes. It's super funny and, 3 minutes or something, maybe 5 minutes long, no longer. There's 3 Kyrgyzstan in a nutshell videos. Many of you know those fascinating animated short 5-10 minute videos about science topics. There's three there about black holes, and then several documentaries, things like neutron stars running into each other and blowing up and making black holes, animations of a star orbiting too close and getting eaten, torn apart by a black hole, the Milky Way galaxy and the Andromeda galaxy, two super massive black holes orbiting around each other and ripping each other apart, as we believe will happen. And I think it's 2 million years from now. I think it's 2 billion years. So, several things there for you, and including one I'll refer to, or a couple I'll refer to towards the end of that list, towards the end of my lecture. And then the very last one there is a simulation of what it looks like, what you might see if you're getting sucked into a black hole. If you personally go into a black hole, what it would look like. And then that's the one I'm going to try and play, and hopefully it won't fail at the very end of this. So black holes are among the most dense, most high energy, most long-lived, information-rich, hardest to create in a lab. That's one of the things we're trying to do with the various particle accelerators around the world, including the one in Stanford, the one in CERN, the one in Europe. Black holes are also one of the most mysterious objects in the world, in the universe. There's no light emitted from them. They're, by definition, unable to share any information. There's no light reflected. There's nothing coming out of them, so we can't really know what's going on inside of them. Partially why we named them black holes. The deal is that the black hole, which has many parts, we'll talk about the anatomy of a black hole, but one of them is we have this mystery in the center, the singularity. That's the black hole. And then at base level, there is one other major part, the event horizon. And we don't think black holes are that simple, but the initial definition is, that's a great starting point. The event horizon is the place at which the density of the black hole is so extreme that as you fall into it, you accelerate faster and faster and faster. And if you were to want to leave, turn around and get out of there, you need a powerful engine that could go faster than that acceleration being pulled in. The force of gravity can be described as an acceleration, and the escape velocity has to be greater. Now, just as with the gravity of the Earth or the Moon or any other object in space, the closer you get to it, the stronger its influence on you. And then that drops off as you move away from it with distance. There's a certain point outside of every black hole. All black holes are different sized, have a unique mass, but there's a certain place where the escape velocity is exactly equal to the speed of light, meaning if you're a little closer than the event horizon, where the escape velocity is the speed of light, if you're a little bit too close, even light can't escape. Even light can't go fast enough to get out of there. And if you're a little farther away, then light can. Meaning within the event horizon, since light can't escape, we can't ever see. And therefore, we don't know what it looks like inside a black hole. Now, I want to talk about escape velocity. So we have an apple here. You like my apple? This is actually a styrofoam ball. So on Earth, I throw the ball up. It comes back down because of Earth's massive amount of matter and compact density. It has warped space and time around it and creates gravity. And gravity pulls things back to Earth. Like I'm right now being accelerated to the center of the Earth, but my chair and the floor are pushing back up on me, and so I'm resisting any motion I might have otherwise. And I can feel my weight, therefore, because of that pull of gravity, is being stopped by whatever I'm sitting or resting on. Okay, so if I were to take this apple and throw it farther, it would go higher. Now, I would have to accelerate it at a greater acceleration. I'd have to speed it up faster, and as a result, it could fight gravity a little longer, go a little higher, and eventually come back down. Okay, and I could continue doing that. There we go. If I'm really strong, it would never come back down. I could eventually throw it so fast that it escapes Earth's gravity. That's what a rocket does when it goes up into orbit. It gets slowed down and slowed down and slowed down, and just as it's about to stop, I mean, it's still going a little bit, as it leaves Earth's gravity becomes so weak that it can continue, and now it has escaped and go, let's see if I can do this. I can't, but in orbit around Earth, right? So for Earth, you have to go faster than 7 miles per second. That's the escape velocity, or 25,200 miles per hour. And if we're talking science geek talk, because this is a science classroom, in metrics, that'd be 11,265 meters per second. Okay, so there's a certain um, velocity. I think that's about 3 times the speed of an average bullet. And if your rocket, the space shuttle, can, in fact, exceed that velocity, if you have enough acceleration that you can fight Earth's gravitational pull and reach those velocities, you can leave Earth's um, gravitational influence and go up into space and orbit around Earth or go to Mars or whatever. Okay, so that's escape velocity, overcoming a gravitational field. Now, black holes form when stars blow up. That's one way they form. Our star, the sun, will not blow up and become a supernova. Stars bigger than our sun might, and then they go through this process where they basically collapse on themselves, and they have light shining out because of the thermonuclear reactions taking place, and that energy pushing out works against gravity, and they become very stable in size for 90% of their lives, and then they start running out of hydrogen in the center there, and fusion changes, and they expand, they contract, and strange things happen. If they ever get to the point where they are fusing bigger and bigger elements and try and fuse iron, all of a sudden the fusion process with iron isn't exothermic, and now there's nothing pushing out against gravity. In fact, iron is an endothermic reaction. It sucks in energy. Now you have gravity sucking in, and then all the nuclear fusion sucks in more, and everything collapses and implodes and rebounds out into space. One of the biggest, most energetic electromagnetic events in the universe, a supernova. And when supermassive stars blow up, the resulting core continues to collapse on itself, and those atoms and electrons get smashed together. The electrons get forced into the nucleus, into the protons, making neutrons. Neutrons are next to each other, but then they get forced into each other, and all this matter gets forced into this tiny singularity. So, for example, we're orbiting around a supermassive black hole in the center of the Milky Way galaxy. Our sun, the solar system, we're all kind of going around every 200,000 years, we think, around the Milky Way galaxy. And that star, supernova, and that black hole, we think, has about the mass of 6 billion suns. 6 billion, over 6 billion times the mass of the star we orbit. But it's packed into a very, very small place, the singularity. So that's what a black hole is. Because it's so dense, its gravity is extreme, and the extreme gravity warps the space-time continuum to such a degree that it can hold multiple stars and solar systems. We think there are 300 to 400 billion stars and solar systems in our galaxy alone, all orbiting this one black hole, all trapped, swirling around the edge of that cone of depression formed by the supermassive black hole, the center of the Milky Way. And for a black hole, of course, the escape velocity at the event horizon is the speed of light. And if you're going the speed of light and you're a little bit outside the event horizon, you could still get away. And even if you're going the speed of light and nothing can go any faster, once you're inside the event horizon, you cannot get away. Nothing can get away, not even light. And that speed of light is about 670 million miles per hour. So this guy, Carl Schwarzschild, was the first person to come up with this and talk about, well, what would this kind of an object be? That's crazy that you could have something within a gravitational field stronger than the acceleration of gravity. This thing would create such incredible forces that it would collapse atoms into themselves and overlap matter in such a tight space. It would be like having an entire sun, but in the size of a marble or less. And he started this whole conversation. He was a soldier in World War One. He was on the front lines, German, fighting against Russia, and he was reading a scientific paper in a physics journal published by some unknown young 20-something named Einstein. And he wrote him letters, and they communicated a little bit. And then this guy, Karl Schwarzschild, was killed on the front lines. And later that year, Einstein proposed this idea to some international union of European physicists. I forget what it's called. And he made sure to say, this wasn't my idea. This guy this soldier, he was an older guy too, he was like 40 or something, 50. This guy was killed on the front lines fighting on the northern front against Russia, came up with this. Interestingly, Schwarzschild means black. Schwarz means black in German, and shield, it looks like Schwartz child. Schwarzschild means black barrier, like a shield. And he came up with the idea of black hole. It almost sounds like his own name. All right, so there's the formula he came up with. It looks almost identical, very similar to Sir Isaac Newton's formula, which we use to calculate, okay, how much force of gravity is there between two bodies? Let's say the first body is the Earth, the second body is the Moon, and so we need two masses, and then we multiply this gravitational constant, which Newton came up with over 300 years ago, and divide it by the distance between the Moon and the Earth. And then we can figure out how much force there is. Well, in this case, same exact thing, except we're not figuring out the amount of force, we're figuring out the distance. And we're not dividing by the radius between them, we're dividing by the speed of light squared. So we have to find out how far away the event horizon is from this black hole singularity. Well, no, that radius is. How far away is it that you have this escape velocity is exactly the speed of light? What you need to know is, what is the mass of the first, I guess these two objects, what is the mass of the black hole? And then multiply that by the gravitational constant by 2, and then divide the whole thing by the speed of light squared. And now you can figure out distance. Okay, how big is that? Now you can think of that distance as not a radius, but like a bubble all the way around a black hole. And if you get closer than that distance, and from any direction around that black hole, if you get within that event horizon, then you are now at a place where the escape velocity is greater than the speed of light. You can't even send out a radio signal saying, help, or wow, it's so cool in here. All right, so that was his math, and we're going to do some right now, which makes you so lucky. This is our last math of the year. We're going to have you calculate some event horizons, some Schwarzschild radii. So SR stands for Schwarzschild radius, which basically means event horizon. Right? When we say event horizon, what we're really talking about is the only way we really have to discuss the size of a black hole, because we don't know what the singularity looks like. We actually know almost nothing about the singularity, what it looks like and what we find there, how the laws of physics work and don't work there. All of our math breaks down so that we find all of a sudden where we've done amazing revelatory insights, or provided all sorts of incredible descriptions and understandings. As you get closer and closer, once you're finally at the singularity, we actually have nothing to say. We don't know what's going on there. And so when we say, well, how big is that black hole? What we're really asking is, well, how big is the event horizon? So we're going to calculate, depending on the mass of a black hole, how big the event horizon is, or the Schwarzschild radius. We're going to use his formula, 2 times the gravitational constant times mass divided by the speed of light squared. Just some multiplication division. You do have to take the speed of light and square it. All right, so the gravitational constant discovered by Sir Isaac Newton is that 6.67428 times 10 to the negative 11th. So it's a small number, meters cubed per seconds cubed times kilograms. Okay, mass is how much mass do we think that object has. The sun has exactly 1 solar mass, and we don't have a scale big enough to put stars and planets on. So when we're comparing things in space, we say, well, how's it compared to our sun? It's about twice as massive. Okay, we'll call that 2 suns, 2 solar masses. So the sun is sort of our standard for that. And for example, I just said the supermassive black hole inside our Milky Way galaxy is about 6 billion solar masses. So we could say, we want to figure out how big is the event horizon for that sucker. Well, we know its mass. We need that number. So that's what the M stands for in green, and C in yellow. C, as you've seen before in other equations, C stands for the speed of light. So we have 2 times the gravitational constant times whatever the mass is of the black hole divided by the speed of light squared. All right, so if the sun were turned into a black hole, boop, there's the mass of the sun. 1.98892 times 10 to the 30th times 10 to the 30th, yeah, kilograms. So 1.9 E30. Now I'm going to show you the math. We're going to do a problem together. We'll do a second problem together. Then I'm going to have you do two problems. And in both cases, I'm going to stop video and have you get the answer and enter it. Okay, so pay attention. You can go back and review this, pause as you need to. So here we have 2 times the gravitational constant. That's the 6.67 e to the negative 11th number, times the mass of the sun, which is 1.9 E30, and that's at the top of the page as well. So I've multiplied all those together. What do I have to divide by? Do you remember? Bing! Speed of light squared. All right. You do that as we've done math in the past. Either you do it online or with your graphing calculator. It's up to you how you want to do this thing. I do it on my phone, and that's the number you should get. It's the same thing. If I were to divide that by 1,000, that 2,948 meters is about 2.9 kilometers. You might be familiar with kilometers, like 2/3 of a mile. So it's about 3 miles, about 3 kilometers. 2.9 kilometers is about 2 miles long. If I were to get the sun and crush it down to the density of a black hole, so all the same number of atoms, all the mass and energy of the sun still exist, but I've made it more compact. And that little snowball sun I've crushed down now will be the density of a black hole, of a singularity. About 2 miles away from that sun would be the event horizon. So this is a relatively small black hole. Let's do another math problem. Let's say that we're going to take the Earth and crush it down and make a black hole. How big a black hole would that be? And again, what I'm really asking is, well, how big would the event horizon around that black hole be? So we're taking all the mass, all the atoms, all the matter of the Earth, including us, I suppose, and we're going to crush them down, make them really dense and compact till they reach the density of a black hole. How big would the event horizon be? There's the mass of the Earth, 5.97 times 10 to the 24th kilograms, or 5.97 E24 kilograms. Okay, here's our formula. That's the first part, 2 times the gravitational constant times the mass. We're going to divide all that by what? Bing! The speed of light squared. You're going to do that magic with your crystal ball, your magic 8-ball, or your phone, or using the computer. You're going to get, hopefully, the same number I do. So our short shield radius, or our event horizon, is 0.00889 meters, which is about, if you were to round that off, that'd be 0.00. If you were to round that up, it'd be 0.01. Right, that 8 we could round up. So 0.01 meters is about 1 centimeter, a little less. All right, here's the first problem for you. So I want you to follow the same procedure, the same formula. If you didn't write it down, you can go back and see it in the video. I'll tell you it right now. To get the short shield radius, or the event horizon, you multiply 2 times the gravitational constant. I'll tell you what, for this first problem, I'll put that much up there before I stop the video. There's the mass of, estimated mass of Lander Valley High School. 2.97 times 10 to the 7th kilograms. We're going to take this massive building, all the atoms it takes, and all the lights and stools and tables and chairs and walls, 2x4s and light switches and toilets and sinks and everything. We're going to take the mass of LVHS and crush it down to a black hole. How big would the event horizon be? We need 2 times the gravitational constant. Now write this down, because you're going to need it for the next problem as well. Okay, I'm not going to bother showing you the speed of light. You can look it up if you don't know it. It should be easy to remember. But so here we have the short shield radius is 2 times the gravitational constant, 6.67 E negative 11 meters cubed divided by second squared kilograms, times this mass I just gave you. Okay, divide that by the speed of light squared. I'll pause right now, and then you give me your answer. Okay, divide by the speed of light squared. Oh, this is how you type it to the internet if you want to do it that way. And here is the answer. I got 4.4 e negative 20 meters. Or that's what it would look like if you drew out all those zeros. 0.000000. I'll let you read it for yourself. That's pretty small. Okay. Another problem for you. What's the mass of you if you're a black hole? Can't quite see the words there because of my picture, sorry. But what's your mass? Now, of course, you have to get your mass and convert it to kilograms. I recommend just go to your phone and type in pounds to kilograms and put in the number of pounds roughly you think you weigh. If you don't know at all and you don't want to use your weight, you can use mine. We'll say I weigh roughly 72 kilograms. I do the rest of the problem, take 2 times the gravitational constant times my mass, divided by the speed of light squared. How big a black hole would you make? Where would the event horizon be if you were crushed down to the density of a black hole? If you want to use me, or what would the event horizon be? The size of that be? I guess it's a radius. If you were to take a person about my size and crush them down and make a black hole out of them. Okay. Did you get the answer? Here's the math problem. Hopefully you set it up right. That's what I got. Basically 1 times 10 to the negative 25th, or 1 e negative 25 meters. It's a lot of zeros. We'd make really small black holes. In fact, this is 10 billion times smaller than a proton. The simplest, smallest atom is just a proton. We call that hydrogen. Sometimes it loses its electrons. 1 proton, 1 electron, boop, it loses the electron. That's the simplest, smallest atom in the world. This would be 10 billion times smaller. You could fit 10 billion of them on 1 proton. And that means if you were to take 10 billion people, crush them down, you could make a black hole the size of 1 proton, the smallest atom in the universe. 10 billion people to make a black hole that size. That's how densely compacted all that matter is inside of a black hole. And by the way, we don't even have that many people on the planet. All right. Nice job. Here's a little drawing. RSCH is radius of the short shield. Singularity is the black hole. So in the center of that circle there is the black hole. We know nothing really about what's going on there. And then you just calculated the size of the event horizon. That was the short shield radius. That's the simple understanding of what a black hole would look like. Now, give you a little more detail. There's an area outside it where light is trapped in orbit. It's just kind of going around and around and around. It isn't sucked in yet. It hasn't gone past the point of no return. But this gravity is so strong it bends even light. And we can see that with eclipses and various things. We can see that in certain situations we'll see a celestial object that's hidden behind some other object in space. But the light will bend and go around that gravitational funnel or well in the continuum of space-time. And so in this case, the funnel, that depression in space-time, the way this gravity, the object is so dense, the way it has warped space itself so tightly, the light itself will just kind of go in circles around it. So that's a photon sphere. It's a sphere of light orbiting a black hole. Now, as you got sucked in, you'd go past that light and be this blinding flash. Here are those parts. Sorry that my formatting got messed up. Singularity, that's the black hole. Event horizon, the point of no return for light. Photon sphere, that's a bubble around the black hole where light is kind of trapped in orbit. But we think that most black holes spin. Most are rotating. We think almost every planet, almost every asteroid, almost every star is rotating. And if this is made from a collapsing star after a massive explosion, so all that kinetic energy, we can't figure out why we'd ever find any black holes that aren't rotating. And when they spin, especially if they have an electrical charge, they get much more complicated. So first off, they end up with 2 event horizons. Here's a simple diagram of what we kind of think that might look like. Basically, the vertical line is showing you, like on a model of the Earth, that's the axis it spins on which it spins. And then that blue kind of a halo going around the center there is a disk of debris swirling around. It's like caught in this whirlpool getting sucked into the black hole, it would look a little bit like the rings of Saturn. Okay, that's the accretion disk. And in between, there are all these things. So going from the accretion disk in, we've got the ergosphere, unstable orbits, still can escape. We have then the outer event horizon, no escape even for light. Then there's an inner event horizon. Remember I said there are two of them. And then there's a singularity. This diagram doesn't show the photon spheres. They would be between the ergosphere and the outer event horizon. And that is still stuff we can see, and it's where light is being bent and trapped in orbit. Okay, so let me just explain that again. Now going from the inside out, singularity, that's the black hole. We have no idea what that is. We know that everything would be crushed, right? We can fit many, many suns inside this thing that might be, we don't know, infinitely small. We think it might be infinitely small. All right. There's an inner event horizon. Sorry that you can't quite see that word. Just outside the singularity. It's orbiting the same direction as that the black hole is spinning. There's an outer event horizon, also orbiting the same direction the black hole is spinning. These are compacted more and tightly to this singularity when we have a black hole that's spinning than if it were stationary. We then have two photon spheres. We have light trapped in orbit. The inner one rotates with the black hole. Then we have an outer photon sphere. Light is trapped in orbit, but this outer photon sphere, the light's going the opposite direction of the black hole, of the spin of the black hole. We have the ergosphere, really interesting. Here we have, bad formatting again, the ergosphere is a place where there's debris and chaos outside of those blinding orbits of light, outside of the point of no return, right? But there, a stable orbit would be really impossible to maintain. You'd have to have, of course, a rocket that could accelerate you almost to the speed of light, because the ergosphere goes right up to the outer event horizon. And you'd have to have this powerful engine, but you'd have to be adjusting constantly. In fact, part of the reason it's so chaotic in there is space itself is getting dragged, they call it frame drag. So here I have a black hole, but it's spinning, it's rotating really, really fast. And it's so dense that it has warped space and time dramatically around it. And as you get sucked into one, time slows down to the point where for you, it becomes infinitely slow and in essence has stopped. It comes to a standstill. So it would take you an infinite amount of time to actually get in there. You wouldn't know that. But if an outside observer watching you would say, wow, look how that just froze at the event horizon. It's not going anywhere anymore. It's because time would be slowing down in that reference frame as the gravity creates this crazy acceleration. Now, the ergosphere, you'd have to have these crazy jets and stuff, and because space itself is starting to rotate and orbit around that black hole. Space is orbiting around that black hole. I guess I have to say space and time. I can't even picture what that means. Okay. Then there's this debris pile of stuff. It's like a whirlpool slowly getting sucked in. That's the accretion disk. That's a cool word, by the way. Torus means donut shaped. So disk, you can imagine like a frisbee shape, or the ring, but the rings of Saturn. You take Saturn away, there's a hole in the middle. So that leaves like a donut shape. That's a torus. Fancy word. Your English teacher will love it. Use it in your next essay. And then if the black hole's rotating this direction, and so there'd be sort of like an axis going north and south right here. Along that axis, there would be jets. Some of this material gets heated up to high speeds, becomes high energy, it gets accelerated, is millions of degrees hot, and it gets turned into electromagnetic energy or creates some, and that stuff can get just blown out. Particularly if too much matter is infalling at once. We'll have stuff shooting out of those jets, and those jets can go, for example, with that picture scientists took last year. First time we got a photo of a event horizon around a black hole was done with radio telescopes. That was a galaxy called Messier 187, and there are jets that scientists, astrophysicists, have been observing around M187 for a decade or more. Really active, shooting 1,000 light years in either direction, up and down. And basically, as the thing is eating, and what we saw at the event horizon is all this hot stuff swirling around. There's so much swirling around and falling in that some of it can't get swallowed. It can't all get swallowed at once, and some gets shot out along that axis. And it can go across multiple galaxies. It can go hundreds of thousands of light years. This would be a lot like if you had a yogurt container, those little plastic jars, and you peel off that foil lid, and you're eating it. It's like halfway gone, and you drop it to the floor. It just falls out of your hand. And as it falls, yogurt's going to come shooting out the top when it hits the floor, right? So if too much matter falls inside the black hole, more than it can actually digest at one time, some of the extra stuff gets spun out and shot out the jets. So there we go. In the center of the singularity. I'm going to review this, and I'm going to pause and ask you to write them down from memory. You can cheat. I don't care. But I want you to have to kind of see if you can generate this list yourself. Singularity is the black hole. Inner event horizon, spinning really fast, same direction as the black hole. Outer event horizon, spinning a little slower outside the black hole. The outer event horizon is the place where the escape velocity is equal to the speed of light. So at that point, and anything closer to the black hole, inside the outer event horizon, even light can't go fast enough to escape. Outside that, we have two photon spheres trapped in where light is trapped in orbit, and light is going around and around the black hole. The inner photon sphere rotates the same direction as the black hole also, and then the outer photon sphere rotates the opposite direction, just a blinding bubble of light, all bending and whizzing around, trapped in orbit around this incredibly dense gravity mass thing. And then we have the ergosphere, crazy unstable orbits, because even space itself is now being drugged and is being forced to spin and orbit around the black hole. And then we have the accretion disk of debris swirling like a whirlpool, or the rings of Saturn, and probably heading towards the black hole. And then when too much is falling in at once, some of the stuff gets ripped apart and shines out as these jets of energy going with the axis of spin, top and bottom, out of the black hole. So singularity, inner event horizon, outer event horizon, inner photon sphere, outer photon sphere, ergosphere, accretion disk, jets. See if you can name all 8 of those things now. Okay, welcome back. I hope you got that. I hope that was pretty easy for you. Singularity, inner event horizon, outer event horizon, inner photon sphere, outer photon sphere, ergosphere, accretion disk, jets. Voila. There are really tiny black holes. We think microscopic. I suppose that's a problem if you're on a spacewalk and one tears your uniform, your spacesuit, and now that's in air. They're impossible to know or to track or to map, but they could cause an accident as we do more traveling in space. I'm going to get rid of all this information and move on. There are stellar mass black holes, meaning black holes that are about the size of stars that have come from stars. Let me get rid of all that. There are supermassive black holes. We think that the center of every galaxy, the nucleus of all galaxies, are supermassive black holes. We think some of these go back to the very beginning of time, as the example of the one in the middle of the Milky Way galaxy, a black hole that we think is about 6.2 billion times the mass of our sun. They're really big. And basically, as they eat more stuff and as more matter falls into them, their mass increases and their density increases and their gravity increases. So they grow with time. And as they bump into each other, for example, we think we will collide with the Milky Way galaxy, will slam into and swirl around and join the Andromeda galaxy, our nearest neighbor, in something like 2 billion years. Well, we think that most of the stars will miss each other. There's lots of them, but they're so far apart. They'll just swirl, make new constellations, and kind of swarm around, make a different shaped elliptical, maybe a regular galaxy. The center of it, though, eventually these two black holes will meet each other and make an even bigger supermassive black hole. They'll join forces and make one black hole. It's kind of what we think. Okay. There's a great video. It's an interview. Maybe it's recorded, with Neil deGrasse Tyson. He's hilarious astrophysicist from Harvard who runs the planetarium, the Fisk Planetarium, I think, in New York. And he's prolific, not only in writing, but also in videos. He's verbally so playful and smart. He's really entertaining to listen to. And you can watch a YouTube video about him. I've linked it, and I think it's the second or third from the end of my list. But you can just search for it. Neil deGrasse Tyson. I've stolen some of his ideas here. I've got a really funny, stupid cartoon of these two cat dog cartoon figures getting sucked into a black hole. I'm not going to show it to you because I don't know if it'll work. From the first Star Trek movie, there was a scene of a black hole being destroying a planet, and I guess it's planet Vulcan, and their simulation, their weird computer green screen, computer whatever the heck, magic Hollywood stuff they did was pretty accurate, pretty reasonable simulation of what physicists predict it would look like if you had a little black hole, and it got into the, let's say that the circle you're looking at, the picture where I am, that is the outside circumference of a planet, and a little tiny black hole gets in there. What would happen is it would look like it's kind of floating around and orbiting in this weird place. And as it's doing that, it's eating up matter and digesting all this stuff. What's really happening is it gets in here, it would start to sink into this planet, and then the planet would try and orbit around it. All that, now the center of mass is wherever that black hole is. So the planet would start this lopsided orbit around that black hole as it's disappearing on the inside, starts caving in, there are earthquakes and things happening, and then eventually it's completely gone as it gets sucked into that black hole. So that little scene is a pretty good simulation. And one of the things I wanted to do a better job including was gravitational lensing. I didn't even include the word well because my picture covers it up. But that's a phrase to describe how light can be bent by gravity. So you can have light going around a planet, or better yet, a star, or better yet, a whole galaxy. So we see in pictures from deep space light coming around. Sometimes we see the image 4 times as it comes around a galaxy. It's in the foreground, and then we can see what is, I guess, hiding behind that because of the way the light of the objects, the galaxies in the background, bend around because of the way supermassive objects will warp space itself. Sometimes what you see is a ring, like a smile, around an object, and that is the light from something behind kind of getting smeared around as it bends and orbits that object. So it's one example of Einstein making a prediction that later we say, oh my gosh, we see it everywhere now. He just has been batting 1,000. Nobody's proven him wrong on any of these ideas yet. I guess I had information right there for you. But I don't think I have a good picture for you, and I'm sorry about that. Well, I've got a poor one. This is the Hubble Deep Space Image, and those smears are galaxies. Some of them you can see are spirally, but some of them are stretched out because of this gravitational lensing, and some of them are repeated multiple times. Sometimes you'll see a diffuse bright spot. It's a galaxy, and it seems like there's a circle around it, and that's an Einstein ring as well. Okay, so there's an image of how a massive object will bend space itself. An image of, if you can imagine, that's a cannonball on a bed or a trampoline, how it makes this depression, and that cone represents space itself being warped and explains why other objects would fall in towards that object, why we are stuck on our planet. You jump up and you fall back down to it. Why the moon is stuck in orbit around us. It's going in a straight line, but it's on the inside of that cone. And so it keeps following the circular path of coming back to the same place and never quite escaping. Cone of depression around a black hole, the object is so dense that that cone becomes almost parallel, and the walls of it are all vertical and so steep that almost maybe tears the fabric of space and time itself. We don't really know. You've heard about a wormhole, and this is important. Heard about it in science fiction. A wormhole, we think, is a theoretical object we've never observed. We don't know if they exist, but mathematically, we know that they are consistent with everything that has been correctly predicted and observed about the theory of relativity. And they're basically two black holes linked. And the idea is that that tunnel in space-time opens up at this other black hole, and you could fall through it and pop out there. The pair of black holes, therefore, would make a shortcut through space. And while it takes light a long time maybe to get from point A to point B through space, that tear through the fabric of space-time would allow you to skip a lot of that and just do it in a shorter distance, and therefore cut down travel time. We don't think you'd survive the trip. I'm going to talk about death by black hole soon. We also have never observed one. That means that the other part of that pair here is like a window where all of a sudden stuff comes shining out of. We think black holes are areas where things disappear, right? Even light can't escape. It just sucks in planets and galaxies and stars and things. Well, a white hole, then, the other end of that tunnel would be a place where these things all of a sudden get ejected and shot out. And we don't observe that anywhere in space. For all of our telescopes and all of our cameras and all of our images, all of our researchers and studies, we've never once seen a place where out of nothingness, all of a sudden, light and energy and planets and galaxies start to appear. But that's the concept of a wormhole, or a Einstein-Rosen bridge tunnel. So we answered this in class. You don't have to answer it right now. Great question. So what would happen to us on Earth if now the sun all of a sudden turned into a black hole of the same size? So it has the same mass as it does now, and it's in the same location. We're orbiting around the sun. All of a sudden, the sun is gone, and there's a black hole in its place, exactly the same mass. And several students in class, I don't remember, I think it might have been Nolan and Ross, answered this question correctly. I think we might have actually hit on it for some reason back in August. And so it might be that it's come up twice. At any rate, here's the answer. We're in orbit around something that has a certain mass and has warped space to a certain degree. We'd still be in orbit around something that has the same mass and has warped space exactly the same, except now it's not a star, it's a black hole. Our path wouldn't change at all. We wouldn't have anything to keep us warm or allow our plants to grow. It would be devastating to our climate. We would starve and freeze, but it would not change our orbit. We wouldn't all of a sudden get sucked into it, which is what most people think. Now, if we were to get sucked into a black hole, what do you think that would be like? Okay, so here's some basics that maybe make sense. Tidal forces are the same forces that create, for example, high and low tide. They're all happening at the same time. There are parts of the Earth right now that have high tide, while there are some other places on the planet that have low tide. And it's all because some are closer to the moon and they feel the moon's gravity more strongly. And some are on the other part of the Earth and feel the moon's gravity more weakly. So those are tidal forces. If you're feeling tidal forces because of a black hole, that's bad. This is, I think, the second to last video I've listed on that slide early in my lecture that has a bunch of YouTube videos. You could search for it yourself. Now, if it's a supermassive black hole, not a star-sized black hole, but a galaxy-sized black hole, right? You'd survive past the event horizon. You would die in both cases. But if you're getting sucked into a supermassive one, the event horizon is really far away, meaning even light can't escape. So you would pass that point where you could not get away, even if you're going the speed of light, but you wouldn't yet be dead. You wouldn't yet be feeling those tidal forces enough to get ripped apart and crushed. Now, I'm going to save the more details of that description for later. I'll allow you to do a little research about that. But I have a video for you. So this is, I think, a 6-minute long video, and I think I'm going to watch all of it. It was made by Andrew Hamilton, who's a professor and a physics researcher at University of Colorado in Boulder. And it was made, I'm betting now it's been 10 years or more. And John Hawley from the University of Virginia made the computer simulation using a supercomputer there in order to bring this to you. And then there have been several copycat videos on YouTube, including some shorter ones, but this has the best description. Now, this could be the end of our video. This could malfunction here, so I'm going to cross my fingers. And what you need to know is at the end of this, I want you to answer one final question. I want you to explain death by black hole. What causes what we call spaghettification, and what does it look like? All right, so here's our description and visual of what it would look like to get sucked into a black hole. Here's a YouTube video coming up. This is the very last one I've included on my list. There, it looks like it's working. I'll shut up now, and I'm going to make this bigger. We will have a little bit of start and stop kind of problem. This is going to play. Now, you're going to have a diagram on the bottom left of your screen, and then you're going to be seeing visually everywhere else what you would see as you get sucked in. This is going to get explained by Tony Darnell here. So listen carefully to how to understand that diagram. I'm worried.
Black holes are among the simplest objects in the universe. They are simpler than stars, much simpler than planets, and vastly simpler than human beings. Black holes are what is created when matter is
Okay, I think what I'm going to say is
compressed into
we're going to do
a
this
very
differently.
small place. They are They are commonly created from the deaths of stars,
Maybe. No.
many times the size of our sun,
Maybe.
usually forming from the collapsed core of a supergiant star after it explodes.
Okay, you can watch that yourself. Journey into a black hole is what it's called. It's also listed early in my slideshow. It's the very last one on the list. Now, I'm going to tell you that it's pretty fascinating, and it is all based on, I think it took him 3 years to really take the math and turn it into a written description. The final thing I would like you to do is research what your death would be like if you got to see that sight ever. If you were the first human ever to get sucked into a black hole. It'd be very cool. Neil deGrasse Tyson coined the phrase spaghettification, meaning you get pulled out and extruded in this long, thin line. So give me some details. What do I mean by that? Look it up and explain to me why. What is this thing about tidal forces? Why is it that you would be stretched? I want a real specific thing. So this may take you full paragraph. So what is spaghettification and what causes it? That's it. Thanks for making it through our entire unit on, well, all of our lectures on the theory of relativity. We have left only a movie and 2 questions about the movie. Enjoy. I hope you get outside, fight off that cabin fever, and you look forward to this movie. It's a great one. Take care. Bye.